So the first thing is getting all the necessary files into your MATLAB folder. So the major things are, once again, the energy pop, the coupling files, and then one of the correlation.m. I generally use the V8. So if you look at this, you see in the red box, I have the HOMO, the OMIN, and the OMAX, and those are values that you need to indicate based on your system. So you want to enter the HOMO, and then the min and the max band that you're looking at. The green boxes. What was that? The green boxes are showing the number of coupling files that we're using. In this case, I'm going up to 1,500. And the blue box is looking at the number of time steps, and much like I think it was Brandon mentioned, you generally want your time step to be the same as your number of couplings that you have. So then when you run this, you get out your RRR file, which I have the visualization of here. This isn't a particularly interesting part of the file to look at because you're looking at HOMO minus 80 to HOMO minus 60. But it was discussed at length at some of the earlier ones what we're looking at here. You would also get your autocorrelation graph and a few to look at and determine if things are going well. And this has the same function as the RRR file that we talked about earlier. So then, much like Ulen, the next step would be to generate the green figures and blue figures. And for these, you need a few more files. You need the energy pop, the RRR, the band out, which Ulen's talked about a bit. This one is one that's not separated out into the two different spins like what Ulen had set up. You also need the 4 master optics file, which should be generated when you generate your OS string file for your system. And then the MATLAB code, which both of the MATLAB codes I'm using you can find in the bin on NERSC, just in the standard bin directory. And much like the last code, we have the HOMO, OMIN, and OMAX, which should be identical to the previous one. And then in my blue box here, I have the IH and the IE parameters that Dimitri and Ulen talked about a little bit. So in this case, I have IH equals to 6 and IE equals 11. So what I'm looking at is HOMO minus 5 to LUMO plus 10. The green box, I have some additional parameters that are the Z step you get from the band out, and the Z size is necessary if you're trying to make the green figures with integration by size by Z. So then, much like the results from Ulen, you get the rates of the relaxation rates, and MATLAB will just pump those out for you. So KH will be the relaxation of the hole, KE is the relaxation of the electron. My middle figure here is a occupation graph. So you notice that my original hole was at HOMO minus 5, and it just cascades until we get to its final position, which in my case, I have slightly degenerate orbitals. So that's why we have some occupation on HOMO -1. And then the green figure over here, which shows the rate of relaxation. I can't see the green figure. The rate of relaxation for the electron in the hole based on their energy. I did not include the graph that Yulin did with the biposition, but it's you get this graph that he did as well. In addition to this, on this, the specific code I'm using also gives out the photoluminescent figure, which is this, and the axes are very hard to read on this. So we're going from -0.5 to 4.5 eV on the y-axis, and the x-axis is a logarithmic time scale that I believe goes from -3 to +3. It might be +2 or 4 actually looking at it. So we see that my primary excitation is around 3.5, and then the right-hand side of this is an intensity graph of the photoluminescence. So we see all these peaks on the bottom here. Those are likely intraband signals. Any questions?
Okay, please join me thanking David. So, any questions to the speaker?
David, may I have a question?
Mm-hmm.
Could you please go one slide back? So, what's the meaning of this yellowish shadow we always see in this kind of figures?
The yellowish shadow?
Yeah, in the right panel.
That is that's the location of the electron in the graph. So where it's more intense, that's where the electron resides.
Oh, okay, I got it.
So you notice in my graph that there's actually a shoulder there. So I mean, if you look toward the top, you see that it doesn't relax immediately, all of it together to the band edge. You notice that some of it continues at like 2.9 eV or so. So that means that there's some process that's slowing down relaxation for whatever reason. And I picked when I made this, I literally just picked my initial conditions at random. They aren't particularly useful conditions to look at, but I thought I saw someone raise a hand.
Yeah, Kia has a question.
Yeah, so in this figure, we are able to see that there is a converge and diverge, like it's converge one section and diverge in another section. Why these things happen?
What do you mean?
You see that it's that the line, the yellow line goes like this and then goes down step.
Oh, this
and
shoulder
then,
thing.
Yes.
Thing that I have here.
Yes.
So that's so this dotted line is the expectation value of the electron in this graph, and it's fitted to the single exponential that Yulin was talking about. So because you notice that there's this, I don't know if you can see the cursor. If there's this continuation of the yellow here into around 2.9, 2.8 eV that goes until almost the edge of my graph. So the green color here is the background. So that's 0. The blue indicates the hole, the yellow indicates the electron. So we notice that where the majority of the yellow drops down at around 1 picosecond. That there's a small amount that continues on past 10 picoseconds. So because of that, we're seeing this shoulder in my relaxation expectation value.
Okay.
You don't see that on the whole, because the whole transfers much cleaner, as did the graphs that Yulin showed.
Okay. Yeah.